So this might seem like a silly question, but how many leaves are on 14 clovers? And we're not talking about the 4-leaf ones, we're just the regular ones. So on 14 clovers, how many leaves would there be? 42. That's awesome. How'd you do that? Pardon me?
With a calculator.
With a calculator. But you had to figure out what to do, right? What to multiply. So this sort of a problem, a lot of students can just do. You think about it and you know what to do with numbers. Because you know that there's 3 leaves on 1 clover. And if you have 14 of them, you must take 14 times 3, right? And you get 42. You can do that with clovers or tricycles or other objects that we're familiar with, but you have trouble when we do it with chemical formulas. So we're going to do it with clovers first, and then we'll do it with chemical formulas. So we can treat this as a dimensional analysis problem. So we've got 14 clovers, and they're asking us for how many leaves. So number of leaves. That's what we're trying to find. Well, do we know how many leaves are on 1 clover? Yeah, we do. 3 leaves is equal to 1 clover. So that's a conversion factor. That means we can go directly from clovers to numbers of leaves. So 14 clovers, 1 fraction. So clovers to leaves, clovers to leaves. And I want clover to go away, so I put that in the denominator, so those cancel out. And then I get this relationship from my knowledge of what a clover looks like. 3 leaves per each clover. So 1 clover has 3 leaves. 14 times 3. Let's try, I had a problem with my calculator. 14 times 3. Okay, there we go. 42 leaves. Everybody okay with that? We do stuff like this all the time in real life. We don't really think about it because our brains just understand that, oh, I should multiply by 3 instead of dividing by 3, right? The units are going to tell us what to do when we're dealing with things that don't necessarily make sense to us because they're too abstract. Now, here's a question. Is this, how many sig figs should that have? Well, 14 clovers. Is there any uncertainty in counting out 14 clovers? No. 14 clovers is a counting number, it's exact. How about this, 3 leaves per clover? Is there any uncertainty in how many leaves there are? No, that's exact. And so there should be exactly 42 leaves. Okay. Don't confuse exact counting numbers with whole numbers. 42 centimeters is a nice whole number, but it's not exact because it's a measured unit. Anything that's measured has uncertainty. Counting doesn't, unless, of course, you get into counting crazy numbers. The census, they're trying to count the number of people who live in Fresno. Is that going to be an exact number? No. You've got issues with that because you've got people moving in and out, but even if you counted everybody in one day, within the course of a day, there's a certain number of deaths on average and a certain number of births, right? And so it's like always changing. And so by the time you finish counting, what you've counted has changed, and so that can't be exact. But we're not going to worry about that. Counting a reasonable number like 14 or 42 is going to be exact. We could make conversion factors using other objects. If we had, say 5 spiders, how many legs would we have? Well, each spider has 8 legs, right? So you can figure that out. A chair has 4 legs. Your mom may have asked you that when you were tipping your chair back. How many legs does a chair have? And that means you're supposed to sit down and put all 4 chair legs on the floor. That's what that means. Your mom does know how many legs a chair has. But if I have 2 chairs, how many legs? 8. Because there are 4 legs per chair times 2 chairs equals 8 legs. We can also get conversion factors just like that from chemical formulas. So here's an illustration of a water molecule. One H2O molecule has 2 hydrogen atoms. So here's the picture. There's 2 white hydrogens and 1 red oxygen. So there's 2 hydrogens per molecule, just like there's 4 legs per chair. We don't need the picture, though. We can look at the chemical formula, and it tells us the same thing. H2O. There are 2 hydrogen atoms in 1 molecule. Do you see how those relate? So the relationships that are hiding in the chemical formula allow us to convert between moles of a compound and moles of one of the elements in the compound. So here is an illustration of a carbon tetrachloride molecule. Here's the formula, CCl4. There are 4 moles of chlorine in 1 mole of this. Just like if you had a dozen clovers, how many dozen leaves? 1 clover has 3 leaves. A dozen clover has 3 dozen leaves, right? So 1 molecule has 4 atoms of chlorine. A mole of this has 4 moles of that. So let's find the number of moles of oxygen in 18 moles of CO2. So write down the number, 18 moles. Now it's becoming more important to write down moles of what? Because we're looking for moles of oxygen and we have moles of CO2. So, a dozen eggs and a dozen donuts and 3 dozen people, and you can't just say dozen anymore because you need to know a dozen what. So 18 moles of CO2, and we're asked to find moles of oxygen. So moles of O. We can do this in 1 step. When we look at CO2, from its formula, we see that 1 molecule of CO2 contains 2 atoms of oxygen. You okay with that? That's what the O2 means, 2 O's. It's also true then that 1 mole of CO2 is equal to 2 moles of oxygen. Just like we could say 1 dozen molecules of CO2 contains 2 dozen atoms of CO2. Of O. Everybody okay with that? So this is our conversion factor right here. 1 mole of CO2, 2 moles of oxygen. 18 moles of CO2, 1 fraction. We're going from moles of CO2 to moles of O. And I want moles of CO2 in the denominator to cancel out. Same dimensional analysis concept. The units are just getting a little weirder. Moles of oxygen to moles of CO2. Well, we figured it out down here. 1 mole of CO2, 2 moles of oxygen. 1 mole of CO2, 2 moles of oxygen. Once you get it straight in your head what we're doing here, do you have to write this down? No. You can just look at this formula. And there's 1 mole of carbon per 1 mole of CO2. There's 2 moles of oxygen per 1 mole of CO2. Yes?
So would it make sense just to multiply 18 and 2 right after that?
Yes, it would give you the correct answer to just take the 18 and multiply by 2. What's important, though, is that you understand why you're multiplying by 2, not dividing by 2, or not multiplying by some other number. And so it's really, really important to be able to show with the units what you did. Because what we're coming up on is something where we're going to combine several of these little steps together. It's called stoichiometry, and it's really important. And if you can do these individual steps, then pushing them together isn't so hard. If you're doing some of this in your head just because it makes sense to you, and, well, if stoichiometry makes sense to you, that'll be great, but most likely not. So, good question. So, 18 times 2, we're going to get 36 moles of oxygen. Now let's talk about exact numbers again. 2 moles of oxygen per 1 mole of CO2. Is that exact? Yeah, it is. Because in the formula, there's exactly 1 carbon atom and 2 oxygen atoms. Because that's what makes the CO2 molecule. So we're going down to the individual molecule level. It's counting a combination of individual particles. Now this one's tricky. 18 moles of CO2, is that exact? No. Because how would we find 18 moles of carbon dioxide? Would we count out? No. It can't be counted because that's a huge number of things, right? When we go from this 1 molecule equals 2 atoms to 1 mole equals 2 moles, we've gone from a counting number to a very big number, but the ratio is the same, and because we started with an exact number, this ratio is still exact. A number of moles of substance is not exact. So here's our answer, 36. I'm not going to try to trick you with stuff like that, but I just want to explain it. Any questions? Okay, so determine the number of moles of oxygen in 1.4 moles of H2SO4. So we've got 1 mole H2SO4, and we want to find moles of O. So we can do that in one step. Look at the formula. In one of these units, how many oxygens are there? 4. The number 4 is just right there, right? O4. So 1 mole of H2SO4 contains 4 moles of O. You may or may not need to write that down. So 1 mole of H2SO4. And I know you could some of you could probably just do this in your head, but it's great to learn how to write stuff down when you actually understand what's going on. So we want to go to moles of oxygen, and I want to divide by moles of H2SO4. And so those cancel. And then I look at what I wrote down here, or I look at the formula, and I see in one of these I have 4 oxygens. So there's 4 moles of oxygen in 1 mole of H2SO4. And this ends up being 4 moles of oxygen. Maybe a stupid problem, but illustrates the use of the units. Any questions? Yes? That's why it ended up being such a stupid problem, because I wrote the number down wrong. Yeah, we need the 1.4. Thank you. Thank you very much for catching that. 1.4 moles. I was answering the wrong question. I think my brain went to mush over the weekend. So 1.4 times 4, 5.6. Yeah, trying to write with an eraser, that doesn't work. 5.6. Thank you. Any other questions?
So when it comes to the stoichiometry, if we just multiply an example like that, would it work with that or no?
If we just 1.4 times 4, it would work, yes. Okay, so that was moles to moles. What if we are converting between grams of a compound and grams of an element in that compound? And this goes back to the beginning question that we talked about at the beginning of this chapter. How many grams of salt could you consume without going over the recommended number of grams of sodium? Because it's going to be more than the number of grams of sodium because there's also chlorine in there. So what mass of sodium chloride contains 2.4 grams of sodium? We need the chemical formula which provides the relationship between moles of sodium and chlorine, not grams. This formula, NaCl, says there's one sodium atom for each chlorine atom. It does not say there's 1 gram of sodium for every 1 gram of chlorine, because the atoms weigh different amounts. The formula gives us the numbers, but we need mass because that's how we count things that are too small to see. So, 2.4 grams of sodium. 2.4 grams of sodium, and what are they asking me to find? The mass of NaCl. Well, mass unit that we use is gram. So grams of NaCl. Do we know the relationship between grams of sodium and grams of sodium chloride? Directly? No. No, we don't. Could we figure out how many moles of sodium are in 2.4 grams of sodium? Yes, we could. We just learned how to do that. We can go from grams of sodium to moles of sodium. Because we know that 1 mole of sodium weighs 22.99 grams. And if we had moles of NaCl, I didn't leave enough space, we could figure out the number of grams, because we just learned how to do that also. And then, based on the formula, we can go between moles of sodium and moles of sodium chloride. So, we start with grams of sodium, moles of sodium chloride to grams of sodium chloride. The path we choose is limited to things where we know the relationship between the two things on each side of the arrow. If I knew the relationship between grams of sodium and grams of sodium chloride, I could do it in one step, but I don't have that information. Could I calculate it? Yes, I could. But calculating that would basically involve doing this. So we're just going to do this. Once you get this idea of going from unit to unit to unit, it actually goes very quickly, and you don't need all kinds of complicated conversion factors. So I've got 3 arrows here. So 2.4 grams of sodium. And then the units here are what I write in the tops. So I have grams of sodium to moles of sodium. The next unit is moles of sodium chloride. And the last unit is grams of sodium chloride. And then I put units in the denominator so that they cancel out. I want those to go away. And I want this to go away. And moles of NaCl. We're going to cancel. Got all the units in place. Units first. I know it's tempting to throw numbers in there and do the units first. So I have 3 terms here, and I need to find numbers to put in there. I think this middle one is the easiest. Moles of sodium chloride and moles of sodium, that all we have to do is look at the chemical formula. This chemical formula, NaCl. In this unit, how many sodiums are there? Just one. So there's one sodium in 1 unit of NaCl. That means there's 1 mole of sodium in 1 mole of NaCl.
Why do you have just 2.4 grams of sodium in the beginning?
Because that's what it gave me up here.
I mean, 2.4 grams, you just have 2.4 Na, not NaCl.
Right, because we're trying to find the mass of sodium chloride that would have 2.4 grams of sodium. So there's 2.4 grams of sodium, and along with that, there's some mass of chlorine that'll give us the total mass of the salt. So if we, the USDA or the whatever, those people that tell us what we're supposed to do, they don't always know what they're talking about. They recommend that you don't consume more than 2.4 grams of sodium. Well, the question is, how many grams of table salt would that be? And the reason they don't tell us don't consume more than such and such grams of NaCl is because table salt is not the only source of sodium. It can come from MSG, monosodium glutamate, has sodium in it, and there's a lot of other things in your food that contain sodium, and so it's the sodium that matters, not the sodium chloride. Does that answer your question? So it's just what the question's asking, really. Because if we had, what's the mass of sodium chloride that contains 2.4 grams of sodium chloride?
You're just working this one backwards.
Right.
Right.
Yeah, so instead of saying, how much sodium is in a certain number of grams of sodium chloride, it's the other way. So 1 mole of sodium chloride has 1 mole of sodium. I think this is the next easiest one because this is an element. 1 mole of sodium weighs how many grams? Where is that number? It's on the periodic table. So 22.99 grams. 1 mole of sodium weighs 22.99 grams. It's on the periodic table. And for this one, here we need the molar mass of the compound. And so we have to look at the formula. So here's NaCl. There's 1 sodium. 1 mole of sodium weighs 22.99 grams. And 1 mole of chlorine weighs 35.45 grams. And we get 58.44 grams. So 1 mole of sodium chloride weighs 58.44 grams. So this is something we just learned how to do this morning. So this is my relationship that I need here. It's 1 mole and 58.44 grams. So I start at the left, multiply by the top, divide by the bottom. 2.4 times 1 divided by 22.99 times 1 divided by 1 times 58.44 divided by 1. And again, some people need to do the multiplying and dividing by 1, other people don't. You'll get the same place. So I should have 2 sig figs and write down 2 more digits. There's that many grams of sodium chloride. And so 6.1 grams of sodium chloride. So if I ate 6.1 grams of table salt, I would get 2.4 grams of sodium. Any questions? So determine the mass of oxygen in a 5.8 gram sample of sodium hydrogen carbonate. And there's the formula. So this is going from grams of compound to grams of element. The previous example was grams of element to grams of compound. it comes down to the same process. So I'm given a number, 5.8 grams of, we should write the formula. And then what are they asking me to find? Grams of oxygen. So I don't know how many grams of oxygen are in a certain mass of this. I don't. Mole is our unit that goes into the middle of almost anything. So if you don't know how to get from one side of the river to the other side of the river, you're probably going to need to step on a couple of moles along the way. So we could go from grams of sodium hydrogen carbonate to moles of sodium hydrogen carbonate. Yes, it gets tedious writing the formula over and over again. Just do it. This conversion is just the molar mass. We just take the masses of each of the elements, we add them up together, we figure it out from the periodic table. And from moles of sodium hydrogen carbonate, we can go to moles of oxygen, and that conversion factor just comes from the formula. We look at the formula. How many oxygens are in one of these? 3. So that's the relationship. And then from moles of oxygen to grams of oxygen, we're going to use the periodic table again. So grams to moles to moles to grams. So then we write this out again as our equation, our mathematical equation, 3 arrows, 3 conversion factors. What we've written here are the units in the numerator. Grams of sodium hydrogen carbonate. Next one is moles of sodium hydrogen carbonate. And then moles of oxygen. And then grams of oxygen. This unit comes to the denominator. So I want that to cancel out. And moles of sodium hydrogen carbonate. I want those to cancel out. And moles of oxygen. I need those to cancel out. Okay? So we have three relationships we need to figure out. Well, we already talked about this one in the middle. Moles of oxygen to moles of sodium hydrogen carbonate. We get that just by looking at the chemical formula. 1 unit of this has 3 oxygens. So 1 mole has 3 moles of oxygen. If you think about a tricycle, how many wheels does it have? 3. Yeah, it wasn't supposed to be a trick question. 3 wheels on a tricycle. If I have a dozen tricycles, how many dozen wheels do I have? 3 dozen wheels. The relationship of 1 to 3 is the same regardless of which counting unit I put in there. If I had a gross of tricycles, how many gross of wheels would I have? 3. A gross is 144. It's a counting number just like a dozen. If I had a mole of tricycles, how many moles of wheels? 3. Okay. I like this one next because it's just the element. Get the number off the periodic table. 1 mole of oxygen weighs 16.00 grams. And then this one's a little trickier. I need to calculate it. So I look at that formula, NaHCO3. I have 1 mole of sodium. 1 mole of sodium is 22.99 grams. I have 1 mole of hydrogen, 1.008 grams. I have 1 mole of carbon, 12.01 grams. You'd look those numbers up on the periodic table. And 3 moles of oxygen, 16.00 grams. 22.99 plus 1.008 plus 12.01 plus 3 times 16 equals. Now, when you do this calculation, that's a lot of digits, of button presses on your calculator. It is super easy to do one of those wrong and come up with an answer that's not quite right. Or to drop your calculator. I'm sure that was loud in the video. Sorry. So when you get this number, will it necessarily jump out at you if it's wrong? No, not so much. So anytime you do a calculation and you really care if it's correct or not, I would encourage you to clear your calculator and then go back and punch it through again. Okay? If you made a mistake the first time, you probably will not make the same mistake again. And so you'll end up with two different values, and that'll say, oh, wait a minute, one of those has to be wrong. So then go for best 2 out of 3. Do it a third time. And then whichever the two that agree, that's probably correct. Okay, that can save you some points on an exam. So we just figured out that 1 mole of sodium hydrogen carbonate weighs 84.008 grams. So now just multiply and divide across. 5.8 times 1 divided by 84.008 times 3 divided by 1 times 16 divided by 1 equals, based on my starting number here, 2 sig figs, 4 exact, 4, so this should have 2 sig figs at the end. 3.3, there's my second significant figure, write down 2 extras, 1.4 grams of oxygen. I'm going to round this, 3.3 grams of oxygen. Any questions?